All right, today we are going to do work-kinetic energy theorem. This first example we're going to do is have no friction and no applied forces. And when those two things are true, we're going to have a conservation of mechanical energy. So not only is this a work-kinetic energy problem, but because friction is zero and there's no applied forces, it's also a conservation of mechanical energy problem. So I have a 3 kilogram block sliding on a frictionless surface at 8 meters per second. It's going to collide with a spring constant of 300 newtons per meter. And I want to know how far is it going to compress that spring before coming to a stop. All right, so we're going to get out our work-kinetic energy theorem. And in order to use that, we need to start with our two basic setup pieces. We need to identify point 1 and point 2. So where does it start? Where does it end? Starts at point 1, ends at point 2. We also need to identify where his height equals 0, so I'm going to call the ground height equals 0. Now I'm ready to narrow down that work-kinetic energy theorem. So since there are no applied forces, work in is 0. Since there's no work done by friction, because friction is essentially 0 here, there's no work done by friction. Because the block ends stopped, kinetic energy 2 is 0. It is moving at point 1, so I do have kinetic energy 1. Since both height 1 and height 2 are the same, so h1 equals h2, my potential energies cancel out, and we did call that height 0, so they would both cancel out anyway. The spring is not compressed or not even attached at point 1, so there's no UEL1, but at point 2, that mass has compressed that spring. So I do have UEL2. All right, at this point, I'm going to rewrite this equation, so I'm left with 0 equals negative K1 plus UEL2. If I'm solving for either of these, I would leave them there. Otherwise, I'm going to substitute. So since I'm trying to find x, that's compression distance, is inside UEL2. Kinetic energy, I'm going to have to substitute there because I have speed and mass. So I'm going to make my substitutions. So I have negative 1/2 mv1 squared plus 1/2 kx squared. We're going to now solve for that x variable. So I get rid of my 1/2s because it's common. Move the mv squared over to the other side. So I have mv squared. Divide the k over. To get x squared, I'm going to take the square root of both sides to get rid of that square. Plug that into my calculator, and I will figure out that it will be compressed 0.8 meters.